Swayam Prabha. Digital India. Educated India.
Welcome back. So let's take example, maybe a couple of examples uh, on this three-phase star delta transformer to understand, to work out what we developed in theory earlier. So this is again this connection we have this connection we have discussed earlier. This is my this side is my HV side, this side is my LV side, this side is star connected, star grounded as is shown here, and this LV side is delta connected, and you see this connection A is to B is to C is to A. So we have analyzed this connection earlier. We know that here in this case in this case the effective turns ratio capital N is going to be, the transformer windings turns ratio is 10:1. So this is going to be 10 root 3. For star delta transformation we had 10 root 3, and for the delta star transformation HV to LV it was N by root 3. So in this case capital N is equal to 10 times of root 3. Now I have connected phase to neutral voltage balanced on the primary side, 100 is to 0, 100 is to minus 120, 100 is to plus 120, and this voltage will become here 10 volts. 100 divided by the turns ratio of the transformer winding, 100 by 10 will make it 10 volt at an angle 0. Similarly, here I will get 10 volts at an angle of minus 120 degrees, and here I will get 10 volts at an angle of 120 degrees. Now this delta side is connected with a star load. Interesting. But this delta side is connected with a star load, and the star load is 8 plus j6 ohms, 8 plus j6 ohms, 8 plus j6 ohms balanced. So I deliberately choose this 8 and 6 numbers because 8 square is 64 plus this is so 64 plus 36, so this is 100. So that means this magnitude of this impedance is 10 ohms. So my calculation is going to be that much simpler, and the power factor corresponding to this is going to be cos inverse of 0.8, which is 36.86 degrees. So some numbers which are sort of easy to work with every time, and that's the reason. Okay, now my question is, in the three-phase transformer shown above, calculate IA, IB, IC, capital IA, capital IB, capital IC. So these are the line currents on the delta side, these are the line currents on the star side, Y side, and then three-phase power delivered to the load, which as a cross check, again let me upfront only say it, that whatever I calculate it on the secondary side, it should match that on the primary side. So let's get going. Maybe, let me just create some space to work here. So I'll get some space to. Yeah, good. Now let us uh, uh, let us let let us let us try to think of the secondary side. Let us try to think the secondary side, because see, there is one delta and one star. This is the source and this is the load. So there are different techniques to analyze this balanced circuit. For example, I could connect this to equivalently by doing a star delta transformation, which you study usually in the network analysis. You can convert this into a delta, and then I would have a line to line voltage connected to a line to line delta. That is one approach which I could do. But I would take a simpler approach. What I would try to say that as far as this load is concerned, I want to imagine this side as a star, as a star connection of source voltages transformed from here to here, and all that analysis, 30-degree phase shift and √3 value and all that I have already done in my previous lecture, so I am well equipped with that. And then I have a balanced star. I have a balanced stars voltage source now on the secondary side, connected with a balanced star load also on the secondary side. Then how big is that analysis? It's just a few minutes thing after I have done this part. So towards that end, I am now going to think that this is the small va, small vb, small vc, and connected like this. Connected like this, corresponding neutral voltage here, and this VA is going to be how much? This VA is going to be 100 by 10, so it is going to be 10 volts. It is see, this line, I'm sorry, this line voltage is 10 volts. This line voltage is 10 volts. So the value, and you remember capital N is 10 √3. So therefore the voltage we are here is going to be, either you can think of it as 100 by capital N, which is 100 by 10 √3, which is same as 10 by √3, and then we have shown that this star to neutral leads this star to neutral by 30 degrees. So therefore this voltage will be lagging by an angle of minus, because minus of 30 degrees. Alternately, the same thing you can also say that, okay, this is 100 volts phase to neutral, so 100 by 10 is 10, that is the line to line voltage on the delta side. So therefore if there was a equivalent star, the line delta is 10 line to if the line to line is 10 and it is a equivalent star, then the line to neutral would be 10 by √3 minus 30 degrees. Or you just directly work from here, because we have already shown that n √3 is the turns ratio and the HV side leads the LV side by 30 degrees. So simply divide 100 by 10 √3 and you will get 10 by √3, and the angle by which it will lag will be minus 30 degrees. And once this is done, this is going to be 10 by root 3 at an angle of minus 150 degree, creating a lag of minus 120 degrees further, and this is going to be equal to 10 by root 3 minus 30 plus 120 degrees. So therefore at an angle of plus of 90 degrees. So I get this circuit here, and actually this will also be at zero potential neutral because everything is balanced here. No current is going to flow through the neutral. 8 plus J6, 8 plus J6, 8 plus J6 and grounded, and this is my IA, same line current IA. I have replaced this with this, but this side is the same. So IA, IB and IC here are going to be the same. So I will get IA, IB and IC. So now very simple, IA is going to be, so this is also 0 volts, though it's not grounded. You can imagine effectively that these two are actually at the same potential. So therefore IA is just going to be equal to 10 by root 3 divided by this impedance is again 10 at an angle of plus 36.86 degrees. I said cos of inverse is 0.8 is 36.86 degrees. So therefore the current is going to be 1 by root 3 at an angle of minus 36.86 degrees, and then IB is going to be A square IA and IC is going to be A times of IA. So I don't have to calculate, if I don't need to again calculate them, you can calculate it and get the exact numbers IA, IB and IC. So or you can add minus 120 degrees here and you can add plus 120 degrees here, and the magnitude of the current, which is 1 by root 3, is not going to change. All right. So this part we have taken off. I'll rub this because I need this space to do my work. So this part we have taken off. Now our job, next task is to calculate IA, IB, capital I mean A is in capital, B is in capital, C is in capital, IA, IB, IC on the primary side. So again I am going to use this concept here that N is 10 root 3 and N root 3 turns out to be 10 root 3 in this particular case, and when the current you go from the LV side to the HV side, voltage increases, current reduces. So therefore IA is capital IA. So let me write this here. Answer I have got 1 by root 3 at an angle of minus 36.86 degrees. Now capital IA is going to be equal to small ia by N. So 10 root 3 capital N. So therefore 1 by 10 root 3, 1 by, yes, so N 1 by root 3, let me use this. 1 by root 3 is the current, and then 1 by 10 root 3 will come here. So root 3 will multiply, become 3 times 10, so 30. So therefore 1 by 30, and the angle is going to be so the current angle is also going to be minus of 36.86 uh, 36.86 degrees. No, it will be just 1 by, so this 10, just let me make a correction here. This voltage here is 10 by root 3 at an angle of minus 30 degrees. So this is 10 by root 3 at minus 30 degrees, and so this is going to be 10 by root 3 at an angle of this minus of 66.86 degrees. I'm just sorry. So this is going to be equal to 1 by root 3 of minus of 66.86 degrees. And now the current magnitude will become 1 by 30, which is correct. When you go from LV to HV side, just like the voltages got rotated in the anti-clockwise direction by 30 degree, similarly the currents also have to rotate in the anti-clockwise direction by 30 degrees so that the power factor remains the same. So therefore this current will become now minus of 36.86 degrees. Okay. Now let's look at the three-phase power delivered to the source. So let me first of all on the LV side calculate PA, and then PB and PC are one and the same. So three-phase power is 3 times PA. So the current is basically 1 by root 3. I'm just doing the watts calculation. So the current PA is 1 by root 3 square into resistance is 8 ohms. So therefore it is 8 by 9 watts, and the same thing is equal to PB is equal to PC, because the magnitude of the square of the current is going to be same. So P3 phase, if I look at the LV side, is 8 by 3 watts. Now let's come to P capital A, and then from once we know P capital A, we know P capital B, P capital C, and then we can calculate the three-phase power, and they should match on the LV side, on the HV side. So in this side I don't have any directly resistance and current, so I have to go by the VI cos phi formula only. And so V is 100, I is 1 by 30. This voltage is at an angle of 0. So if I draw V capital A, I capital A is lagging by minus 36.86 degrees, this phi. The power factor between the two sides has not changed. So the cos of phi is going to be equal to 0.8. Cos of 36.86 is 0.8. So therefore this is 110, so 8 divided by 3 watts, yes, 100 divided by 1 by 30 into 0.8 is 8 divided by 3 watts. So PA is 8 by 3 watts. So PA plus PB plus PC, the P3 phase is going to be equal to 8 watts. So looks like I have done a small calculation error somewhere here, because both sides should match. Let me check. PA is 1 by root 3 square into 8. So 1 by 3 into 8, okay, I have written it 8 by 9. I am sorry about this errata. So this is going to be 8 by 3 watts, which is equal to PB, which is equal to PC. So therefore P3 phase LV is going to be 8 by 3 into 3, which is equal to 8 by 3 into 3, which is equal to 8 watts. So you get P3 phase 8 watts. Similarly, you can see that P3 phase, or rather QA will be equal to 100 into the current, which is 1 by 30, the current IA, which is 1 by 30, into sine of phi, which is 0.6. So sine of phi is 0.6. So therefore it is going to be 10 by 3 into 0.6, or basically 2 volt amperes reactive. And so Q3 phase HV side is going to be 6 volt amperes reactive. Now the same thing you should get if you do this calculation here also. So what is my IA? 1 by so if I go on the LV side, so the voltage has become, how much has the voltage become? The VA has become 10 by root 3. So small QA is, VA is 10 by root 3. The current value is 1 by root 3, and the power factor is the same. So the sine phi is also again here also point this thing. So therefore it is 6 by 3, which is 2 volt amperes. And so Q3 phase LV is also 3 times of this, which is 6 volt ampere reactive. So again, just like the P story has matched, similarly the Q story has also matched, and so this problem is fully sorted out. Let's take one example. A 3-phase transformer has 400 turns on the primary and 40 turns on the secondary. So the turns ratio of the basic transformer is 400 is to 40, that is 10 is to 1. The supply voltage is 1732 volts. This is not a standard voltage. I have picked this number just because root 3 factors will work out nicely. Root 3 is 1.732. So just to keep my numbers simple, I have picked up this number. Find the secondary line voltage on no load when the windings are, two types of connections are given, Y delta, delta Y, and so in fact you could even talk of YY or delta delta, even you could think of these connections also. So these are the 4 connections. Really this is not about the phase shifts, very simple problem. Find the secondary line voltages on no load when the windings are connected as follows. Okay. So let us take the A part. So 1732 volts comes across the y. So, that is the line to line voltage on the y side. So, therefore, if I take the phase voltage, it will be divided by root 3. So, therefore, it will turn out to be 1000 volts, because root 3 is 1.732, and if I multiply 1.732 by 1000, I will get 1732. So, this is nothing but my V 1, the primary side. So, the V 2, the secondary side, you can V P, V S, that is another thing that you can do. So, you have 1000 divided by V 2 equal to 400 divided by 40. 400 is the N 1, 40 is the N 2, and so this is 10. So, V 2 is going to be equal to 100 volts. Now, the secondary is connected in delta. So, whatever is this terminal voltage coming across the transformer, the same voltage will also be the line voltage. So, therefore, this V 2 is the line voltage on the secondary side. Wonderful. Now, let us take the B part. The primary is in delta. So, therefore, and what you get on the secondary is the star. So, this 1732, because the primary is in delta, this 1732 is completely applied across the transformer, the N1 turns. So, therefore, 1732 divided by N1, this is the EMF per turn, and remember the EMF per turn on the primary side and the secondary side are going to be one and the same. So, therefore, 1732 by N1 will be equal to, now let us say the secondary side line voltage is V 2. So, divided by that root 3, divided by that root 3 will be the phase voltage, phase to neutral voltage, and that is the voltage which is coming across the secondary turns of the transformer. And so, the EMF per turn will be V 2 line divided by root 3 N 2. So, therefore, you have 1732, I am writing is as root 3 into 1000, then I am going to take this root 3 on this side. So, I will get another root 3 coming here, and then this N 2 I am going to take it on this side, N 1 will remain below as it is. So, I will get N 2 by N 1 will be equal to the secondary side line voltage, which is, what is this, 3000 into 40 by 400 is the V 2 line to line, which is going to be equal to, so V 2 line in this case is going to be 300 volts. So, you have got the second answer also done. Let us take YY. So, in case of YY connection, 1732 is the primary voltage divided line voltage divided by root 3, that 1000 voltage is the phase voltage. This appears across the N1 turns. So, this divided by N1 is equal to, if secondary side line voltage is V 2 divided by root 3 is going to be the phase to neutral voltage, and this comes across the N2 turns, and this becomes the EMF per turn. So, therefore, this root 3 and root 3 will cancel out, and I can write V 2L as 1732 by 1000 will turn out to be 1000
volts 1000 into N2 by N1. No, I'm really sorry, because this root 3 has cancelled with this. So, the 1732 will remain as it is. So, I should write it here as 1732 into this N2 gone up here, N2 by N1, which is same as 1732 in 40 by 400, which is 173.2 volts, is it not? So, the turns ratio is 40 400, yeah. So, 10:1, 1 by 10, yeah. So that is correct. So, you will get 173.2, yeah. Again here 1 by 10, that is also correct, and I think here 40 400. So, 10 turns ratio, yeah. So, 100, again it is correct. So, no problem. Then the last one, the last one is it is a delta connection. So, 1732, which is the line voltage, is also applied across the N1 turns, because the complete one comes around the transformer primary, and the V2L, because the secondary is also delta connected. So, V2L is also completely appearing across the turns of the secondary. So, therefore, per turn V2L by N2, this is the EMF per turn. So, therefore, in this case 1732 into N2 by N1, which is 1732 into 40 by 400, which is 107.3.2 volts, will be the line to line voltage. So, this simple example, but still I think we needed to go through it once to get through how to work with the line to line voltages and phase to neutral voltages for different star delta connections. In this example, we have not really worried about the phase shift, 30-degree phase shift, which will be happening. Okay. So, today I am going to take up a topic which is how if load sharing happens between two transformers if they are connected in parallel. So, I am going to work out a small example hopefully and show you the some subtleties. The point is like, let us say you have a residential complex and it is having a 100 MVA load. This 80 square plus 60 square under root 80 square plus 60 square under root is going to be 100 MVA or 100 KVA, whichever way that is. Since I have taken voltages in KV, my load should be in MVA. So, now this load I can supply through one transformer of 100 MVA, or I can supply it through two transformers of 50 kVA, 50 MVA each. Which is a preferred method to do that? Well, from the reliability perspective, I would prefer that I split it between two transformers of 50 MVA. Why? Because devices will fail. As engineers, you would always have to plan for anything which is there is some kind of a fail safe feature in it. Look, in your cars also you have 4 tires and then you carry one stepney also in addition to that, right. So, you provision for the failure of one tire. With bikes, of course, you do not provision for it, but then probably you go for tubeless tires or something like that. Otherwise, you suffer more if you do not provision for in your design. If you do not provision for failures, you essentially end to suffer more if there is a problem. And electricity being a essential commodity or supply, the reliability or redundancy is something that is given high importance while designing electrical systems. So, in this case I could of course go for 3 transformers also, that nothing wrong with that. It depends upon space and other considerations. At least for 100 MVA transformer load, at least I would provision for 2 transformers. Ideally, even this is not a good thing, because if one transformer fails, I will still have to do a load shedding to the to around 50% load shedding I will have to do. But for this example, at least let us work with these ideas, that I have provisioned for 2 transformers of 50 MVA. If I had provisioned for 3 transformers of 50 MVA, then one transformer failing of course will not create any problem. I would be able to supply 100 MVA straight. In spite of it, I would be able to supply the 100 MVA of load. So, the point that I am trying to sort of make is the reliability comes with a cost, and because there is a cost, you should not design reliable systems is a real stupidity. That is not at all what I am trying to sort of say. You should willingly accept a cost and understand that that cost is for reliability. Just like insurance, insurance, you pay a premium for the insurance, it takes care of something else. When you get hospitalized, you take medical insurance, you take car insurance. Here the insurance is in terms of extra redundancy in the equipment that we provide, especially while designing utility services. There are 2 different things. You can be a minimalistic when you are at your home, but if you carry the philosophy of minimalism and design public infrastructure using that philosophy, then you will end up with what you see today: overcrowding of roads, inadequate infrastructure, and that basically comes from the point that we are not willing to pay the price for the cost, we are not willing to invest the cost for the redundancy which is required. So, as engineers, this point I really want to, from the bottom of my heart, I want to emphasize to you that if you are designing something which is a public infrastructure, then it has to be designed with enough amount of redundancy, so that in case of any failure, people are not impacted, 1, and 2, you will not get into congestion as we see in the Indian roads traffic conditions. Electrical networks are much better. The road networks are in a horrible, both are transportation network. One is carrying electricity, another is carrying people in their cars, scooters, trucks and so on. The other one is so poorly done. Even electrical infrastructure was quite poor in the early 80s and 70s and so on. It was in a very bad shape. It has come down, it has improved significantly, because when people were subjected to so much of power cuts, they realized the problem of it. And now there is, at least in our transmission grid, there is adequate amount of redundancy, though I am not sure if it is there till the last mile. I am not sure if it is there till the last mile in the distribution lines and wires and so on. So, but at least the bulk power transmission is not impacted. So, even if there will be a problem, it will be only in a pocket, and it will not be felt everywhere. So, again coming back to this philosophy, instead of going for 100 MVA transformer, I would ideally recommend in this design, to reliably supply 100 MVA of load, 3 transformers of 50 MVA. But in this example, I am taking 2 transformers. Now, ideally, of course, when I go and buy in the market, I will buy the 3 identical transformers. So, I should not have a problem. But suppose for some reason the 2 impedances did not match. One impedance is 3% here and another impedance is 4%. Now, what is percent impedance? That must be a question that must have come in your mind. I will explain that as I go further. There is a generator, it is supplying the power. There is a step up transformer which steps up from 11 kV to 66 kV, and then there is a load of 100 MVA. Again 80 and 60 are nicely picked up numbers, so that 80 square plus 60 square under root is 100 MVA of load, which is being supplied here, lagging power factor. Question is, if the transformer impedances were identical, then of course the current would share equally between them, and if the current shares equally between them, then this 100 MVA load will be distributed as 50 MVA on this transformer and 50 MVA on this transformer, and both the transformers would be loaded 100%, and there would not be there would be best utilization of equipment and complete supply of power. But now what happens in this particular case, that one transformer is having a slightly lower impedance shown here as 3%, and another transformer is having here a slightly higher impedance which is shown as 4%. Then the question being asked is, will the two transformers be loaded equally, or will the two transformers have different loadings, and if there is a different loading, then is any transformer overloaded. So, first of all, I mean, we can think of just a transformer as having one leakage reactance ZL1 here, which is actually XL1 only, because I have not taken resistance, and ZL2 here, and this is connected to a generator. This is connected to a generator, and this side is connected to a load. So, now the voltage drop, this is, think of it as 3 single phase transformers, so that you will not have confusion in your mind as to what is happening. Now, really speaking, the voltage drop is where, means you remember this, we can think of these devices as ideal transformers having a leakage impedance or ZL1 and leakage impedance ZL1, and the other having a leakage impedance of ZL2. So, these are basically this thing, and if this turns ratio is N1 is to N2 and this turns ratio is also N1 is to N2, and suppose that I refer everything to the primary side. So, everything is referred to the primary side, then this actually what I have done is, I am sorry, one minute, what I have done is, I have said that ZL1 is the impedance referred leakage impedance referred to primary side, and ZL2 is again the leakage impedance referred to the primary side for the second transformer, and this load is being shared between the two. So, there is a load which is being effectively coming here, and there is a load which is effectively coming here. So, I will use small l1 here and small l2 to show leakage, and small l2, and this is say load as ZL1, ZL2. Then the equivalent circuit is ZL1 for the first transformer, supply, and this philosophical discussion I am doing, still not playing with numbers, ZL1 N1 by N2 whole square. So, remember I had said that transformer impedances, when you refer it from primary to secondary, this is what is going to happen, and this will be if there were two, if this was not like one bulk load, but two impedances in parallel or something like that, then I could have shown this as shown it something like that. So the point is, you can therefore calculate the load current. Really speaking, you can actually calculate the load current which is coming to these transformers. Now, the drop is only happening where, really speaking, the current sharing, difference in the current sharing is happening because of the difference of these numbers ZL1 and ZL2, but this side it is not like this. These are not two independent transformers like this. What we are having is, when we show them as parallelly operating, what we are having is, this is connected together and taken out as 1, and let us say this is connected together and taken out here, and then a load is connected here. This is actually what is done, not what I have shown here, but this is what actually is done. Similarly, these two terminals will be connected here in together as 1, and these two will be connected, the lower ones will be taken as 1, and this is how the parallel operation will be taking place. So, if this is the way parallel operation is taking place, then what is going to happen is that, see, this voltage is same because this is across the loads and they are in parallel. So, therefore, these two voltages are also going to be same, and this side also the primary voltages are same, and the voltage drop is sort of happening in the basically in the leakage reactances which are shown here. So, if I try to draw the equivalent circuit, I can think of this equivalent circuit as this, whatever I said 6%, I will come back to this, not 6%, I said 3%, and I said this as 4% leakage. This is the supply, and this here is the load. So, this is how the equivalent circuit will look like. Now, this, what does this 3% mean? This you will see a lot more of this when you study power system course, but what it sort of means is, suppose I have a 50 MVA transformer and it is this is 3-phase transformers. So, these are 3-phase transformers, assume they are star star. So, the single phase will be 50 by root 3, the single phase is going to be 50 by 3 MVA, and 11 by root 3 is to 66 by root 3 kV transformer. So, if I call this as the base MVA, there is a notion called, whenever we say something as percentage, it has to be in percentage of something. So, if I call SB as the base MVA, B indicating base, which in this case is going to be 50 by 3, then, and this I call it as the base voltage on the primary side, and this I call as the base voltage on the high voltage or the secondary side, then I can talk of base current on the primary side as 11 by root 3, which is VB1, and base current on the secondary side, which is 66 SB divided by 60, SB is how much? 50 by 3, SB is 50 by 3 and 60 by root 3, and this is MVA. So, this is kV. So, therefore, this is in right now in kiloamperes. So, I can calculate two base volt, one base MVA, two base voltages, primary secondary side, the nameplate rating, then corresponding to that the two base currents, primary side and the secondary side, and then I can talk of base impedance. I can talk of base impedance, which is base impedance is, so base voltage divided by base current. This will be called as base impedance on the primary side, because I have taken primary side base voltage and primary side base current, and I can also talk of the secondary side secondary side base impedance. Now, they are related, this base impedance and this base impedance is base impedances are related. So, this is what VB1 is what? N1 by N2 times of VB2, and IB1 is what? N2 by N1 times of IB2. So, therefore, this is what this ratio VB1 by IB1 is N1 by N2 whole square VB2 by IB2, or in other words ZB1 is N1 by N2, let us call it as A square ZB2. So, now see what happens when suppose I have a load impedance ZL on the on the secondary side, then in per unit, if I ask, per unit means basically ratio of two quantities, the lower quantity denominator is the base, the numerator whatever you have, then like if you get 66 marks out of 100, then your per unit marks are 66 by 100 or 0.66, that is your per unit mark. Percentage is 66 by 100 in 200, which is 66%. So, per unit and percentages are very closely connected values. So, if I have load impedance on the secondary as ZL, then its per unit impedance, I can talk of per unit impedance, which is this is referred to secondary, and this will be a dimensionless quantity. If I compare two ratios of the same type ohms by ohms, it will be a per unit, but you can call it per unit ohms if you want, but actually it is a per unit quantity. Now, the look at it, suppose I refer this impedance. So, this is the per unit impedance, this is the per unit impedance of the transformer referred to the secondary side. If I go to primary side, the load impedance will become A square ZL, and I just showed to you that ZB1 is also A square B2. So, when if I want to do this on the primary side, so this will be the impedance will be A square ZL by A square ZB2, ZB1 is A square ZB2, which is same as ZL by ZB2, which is same as the per unit impedance Z per unit impedance of the load on the secondary side. So, the per unit system with transformers gives you this very important advantage, that 1 per unit low voltage, see 66 kV, 11 kV by root 3 is 1 per unit voltage here, it becomes 1 per unit current voltage on the secondary side 66 by root 3. So, 1 per unit voltage on the primary side, if you do talk in per unit, voltage on the primary side is 1 per unit voltage on the corresponding by turns ratio, the voltage in the per unit system voltage on the secondary side is also 1 per unit. the load here, for example, the load here is so there is some load on the per unit on the on the secondary side, the same load will appear as per unit load in the primary side also. So this is what I just showed you, that the load in per unit on the primary side and load in per unit also in the secondary side is same. The MVA on the primary side and the MVA on the secondary side is same, and MVA base is common for both primary side and the secondary side. So, load even when expressed in MVA, this is also going to be the same for the two sides of the transformer. So, really speaking, then what happens is, I can write this transformer 3% impedance. So 3% impedance means what? Leakage impedance is 3%. If you are doing all the calculations on the primary side and in ohms, then take this as the leakage impedance. This is referred to primary. If you are doing all calculations referred to primary, if you are taking all calculations referred to secondary side, then multiply this by 3% will be 3 by 100, 0.03 into ZB2, the base impedance values. This take this as the actual impedance in ohms referred to the secondary. But if you are doing it in per unit only, just write this as 0.03 and just write that other transformer was having a impedance of 0.04. So, just write it as 0.04 and write this. So, in this case you have to calculate the base impedance using 50 MVA base, because all these numbers are given on the transformer nameplate rating of 50 MVA. I do not need to actually calculate that number, but I am just telling you. Now, suppose this load is, however, on together they are making 100 and this load is on 100 MVA. So, from the load side, if I want to look at it, when I am doing a system level study, I have to, every equipment may have different rating, but as system I will take one base. So, in this case I would sort of say that my system base is 100 MVA. So, if my system base is 100 MVA, and I am going to copy this figure now and take it down, my system base is 100 MVA. So, this is 0.8 plus J 0.6 current. Why is that J 0.8 plus J 0.6 current? Because this is 80 MVA, 100 MVA is the base. So, if the voltage is at 1 per unit 66 kV, then and the base is also 100 MVA, then the current is also going to be 1 per unit. So, 1 per unit voltage into 1 per unit current will give you 1 per unit MVA, but 1 per unit MVA is actually 100. So, this voltage we are holding in our example at let us say 66, load voltage is let us say being held at 66 kV. So, then this current is going to be 0.8 plus J 0.6. So, this current is going to be J 0.8 plus J 0.6 per unit, and you just get a feel for it, first year, first time when you are doing it, try to get a feel for it. Then subsequent years you will be diving more deep into these concepts. This voltage being 66 kV 3 phase or 66 by root 3 V is being kept at 1 per unit. Obviously, this will not be 1 per unit now, because there is a drop when the load current flows, there is a drop. So, this will change. So, we know this is 1 per unit, we know this is my load. So, the current is basically what is Vi star is equal to 0.8 plus J 0.6 in per unit. This is taken as reference secondary. So, this is 1 per unit. So, the I is going to be 0.8 minus 0.J6 per unit. So, this current here I is 0.8 minus J 0.6 per unit, and nothing to worry about. You know what is 1 per unit current on the primary side, you know what is 1 per unit current on the secondary side. So, if I ask you the question what is the current in amperes with referred to primary, multiply it by the base current from the primary. If I ask you what is the current this per unit current, how much does it translate in amperes or kilo amperes when referred to secondary, multiply it by the base current of the secondary side. But for calculation there is, this is the thing. Now 3% I have given you impedance and 4%. So, that means if the base, if 50 MVA was my base, I can just substitute J 0.03 and J 0.04 as the leakage impedances here. But because my base is 100 MVA, system base is 100 MVA. So, if I keep the voltage base same and double the MVA base, what will happen to the current? Current base will double. If the current base doubles, voltage base is same and current base has doubled, then what happens to the impedance base? Impedance base will become half. If the impedance base becomes half and actual impedance whatever it is there is the same, but the base impedance became half, then per unit impedance what will happen? It will double. So, therefore, if I refer the same circuit on same this thing on 100 MVA base, I will write this now. What I will show is, I will show that this is 0.03 will double and become 0.06, 0.04 will double and become 0.08. This voltage here is 1 per unit angle 0. This current which is coming out is 0.8 minus J 0.6 per unit. And now my question to you is, what is this current IL1, what is this current IL2 in per unit, given that IL1 plus IL2 is 0.8 minus J 0.6. So, now if this impedance is called Z1, this impedance is called Z2, then I know that Z1 IL1 is equal to Z2 IL2, because the voltage, this is a per phase circuit, because the voltage drop has to be same, you know, when something is connected in parallel. So, therefore, the currents will share in inverse proportion to the impedances. So, therefore, IL1 will carry, because IL1 is for to get the same voltage drop and its impedance is less, it has to carry higher current. So, IL1 by IL2 is going to be equal to 0.06 and 0.04. So, this is 0.08. So, 0.08 by 0.06, which is 4 by 3 of the 4 by 3 of IL2. So, now IL1 plus IL2 has to be equal to 0.8 minus J 0.6. IL1 is, IL2 is, so IL1 is 4 by 3 plus 1 times of IL2, which is 0.8 minus J 0.6. So, 7 IL2 is going to be equal to, IL2 is going to be equal to 3 by 7 of 0.8 minus J 0.6, and IL1 will be equal to, IL1 will be 4 by 3 of, IL1 is 4 by 3 times of this. So, 12 and 12 by 21, 4 3s are 12, 7 3s are of 0.8 minus J 0.6. So, now it is very clear, it should be clear to you. See, ideally if the two transformer impedances were equal, then the current should have come out as 0.4 with equal leakage impedance. The current sharing should have been half on both. So, point j minus 0.4 minus j 0.3 is what it should have come, but this one is coming to be multiplying and dividing it by 2, 6 by 7 of 0.4 minus j 0.63, and this one is 24 divided by 24 of 0.4 minus j 0.6. So, therefore, there is a overloading, this number being higher than 1, there is a overloading on the transformer with lower lower leakage impedance, and there is underloading on the transformer with higher leakage impedance. So, this 100 MVA, if it was shared as 50 MVA and 50 MVA, it would be perfect, but we are now supplying 100 MVA only, but because this carries 75%, this carries the current ratios, this carries only 75% of the current. I am sorry. So, this there is a IL2 by IL1 ratio, basically what I am saying is 3 by 4. So, this transformer is not going, and the current is less. So, it carries this 75% of this current, it carries 75% of this current, voltages being the same, the MVA load is 75% of this particular transformer. So, this you work out the actual numbers straight away, this you work out the actual numbers straight away, but it is now clear to you that this transformer is underloaded by 50 below 50 MVA, and this transformer will be overloaded, and the loading will go above the 50 MVA, and this is going to cause you this is going to cause the overloading of the transformer. So, how will you calculate that? You know V is 1 per unit. I have already worked out the currents here, is it not? So, just V I star. So, 1 per unit into IL1 star, calculate it, this is, and then change it to MVA. This will be the loading on the transformer 1 with the lower leakage impedance overloaded, and currents are going to be picked up in per unit from here, and 1 per unit voltage, because secondary voltage is kept at the rated value. So, this will be the IL2, you have already calculated these numbers here, then translate it into MVA, and I think you will get around, you will get the, and then convert it into MVA. So, you will know the MVA loading of the second transformer, and so from there I think you would find that this transformer is 14% underloaded with respect to this. So, this is not an acceptable thing. So, another transformer is running 14% above its rated capacity. This will damage the transformer, overheating, and many other problems will come. So, parallel operation either should have parallel operation of transformers either should have properly identical impedances, or we have to, there is on transformer something called as transformer taps to alter the voltage levels, and we have to put this in a boost mode to reduce this current here. So, the net take is the other tap changing, maybe I will consider it some other time permitting, but the important take is
if the two transformers have same nameplate rating, it automatically in terms of MVA, it does not mean that they will and their primary secondary voltages are same, it does not mean that the current will distribute equally across them, unless their leakage impedances are also identical. If the leakage impedances are not identical and you try to run it to the full capacity, each means the sum of the two capacities load, one transformer will get overloaded, which is unacceptable. So, then you have to either correct it by using some controlled methodology, which we can discuss later on, time permitting, or basically just buy something which is appropriately matched. So, let us stop here now. Thank you.